So we're done with all the voids and structure of all the different ionic compounds. Also, the last class which we discussed exclusively were defects, the Frankel and all those 3 types of defects that we discussed. Next, we are starting with the properties of solids. Properties of solids. I also mentioned in the previous class the 3 types of properties that we will be discussing. One is the electrical properties, magnetic properties, and the dielectric properties. So these are the 3 that we are going to discuss. We will go one by one. So let us first discuss the electrical properties of the solids. In the electrical properties, generally, the electrical conductivity, whatever is there, especially in solids, they may arise through the motion of electrons, right? That's how the conduction of electricity is generally happening, through motion of free electrons and through the positive holes or through motion of ions, right? So remember that. So I think I don't need to write that basic thing now, because okay, maybe like electrical conductivity may arise through the motion of electrons and positive holes, or through motion of ions we say ionic conductivity, that is, so ions. Remember that conduction through electrons, if it happens now, if the conduction is happening through electrons, you call this as n-type conduction. It's a very detailed note I want to copy. And if the conductivity is happening through the positive holes, this is called the p-type conduction. We already discussed in different chapters that if at all there is any electrical conductivity happening in the metals, it is due to the motion of electrons, and the electricity conduction is going to increase if there is more availability of number of electrons, so that they participate in this whole conduction process. Okay, that is metals may, there is conduction due to electrons, conduction due to motion of electrons. Whereas in pure ionic solids, conduction takes place due to motion of ions, and wherever the conduction takes place only through motion of ions. And you know, ionic solids, they directly do not conduct electricity except in molten state or in aqueous state. Sorry, conduction of so that is the reason there. Also, this point that I want to write here, as there's no space on the top, is the continuation. So the presence of defects in the crystals it's going to increase the conductivity as there's more space. Let me know once you're done copying this. Let me know. Are you done? If I get a yes, I'll go forward. Through chat box. Tanishq is not present today, I think. Otherwise, at least you would answer. Yeah. Okay. So on basis of the electrical conductivity, we have divided the solids into three different things, right? That we already know. The three different, they are classified. Solids are classified into three types. And this classification is based on the electrical conductivity. Obviously, first of all, the conductors, insulators, and semiconductors. Don't think I'm telling you the basic definitions of them. We are talking according to the solids here. So what happens? Conductors, what do they do? I'm not writing the basic thing. That is, they try to allow the maximum portion of the applied current to flow through them. And their conductivities is what I'm writing now. Their conductivities are in the order of 10 power 4 to 10 power 7 ohm inverse meter inverse. Okay. And as we know, metals are examples of conductors. They specifically are going to have 10 power 7 ohm inverse meter inverse. Insulators, you know, they do not practically allow the electric current to flow through them. So the electrical conductivity is in the order of 10 power minus 20 to 10 power minus 10 ohm inverse meter inverse. And the semiconductors, they will be generally intermediate, now 10 power 6 to 10 power 4 ohm inverse meter inverse. And also remember, and you need to write their semiconductors. So semiconductors generally, okay, these are solids which are perfect insulators at absolute zero. But they conduct electricity at room temperature. So, and semiconductors are divided into two things. Semiconductors are classified into two things. One is intrinsic. Two is extrinsic. So what happens at 0 Kelvin? At 0 Kelvin, pure silicon and germanium, they act as, what are intrinsic first of all? They are semiconductors, obviously. They are semiconductors due to thermal defects. Extrinsic are acting as semiconductors due to impurity defects. That is the major difference. Next comes at 0 Kelvin, pure substances like silicon and germanium, they actually act as insulators because electrons fixed in the covalent bonds are like completely bonded, no electrons for conduction. But at high temperature, some of these covalent bonds are broken and the electrons are released because of this higher temperature, and they become free to move in the crystal, and thus then they start conducting electricity. You understood, no? So what is happening here? Like at certain temperature, intrinsic is Like at 0 Kelvin, if metal, if at 0 Kelvin, silicon, germanium, they act as insulators. Okay. Why? I mean, not purely substances of or compounds of. So because of covalent bonds, means they're completely bonded, no free electrons. Then, but at high temperature, bonds break and electrons are released, which are responsible for this conduction. I'm not able to write about the extrinsic. So once you're done with this, I'll go forward. Are you done? Can I get it done? Yes. Anything which gives me a signal that you're all writing it. So next we have the extrinsic. As I said, this is due to the impurity defect. What happens here? Generally, the conductivity of pure silicon and germanium is very low at room temperature. That's why it doesn't conduct until you send heat. But it can be increased by doping with impurities, which producing N-type or P-type semiconductors. I told you what they are. So once you're adding the impurities, that's going to help in increasing the conductivity. So I hope you might have like written it now. Next we have the magnetic properties. Magnetic properties. You know what is magnetic property generally. So the magnetic properties are how did they actually make a study on this is in terms of their magnetic moments. Like how did we calculate or on what basis are we talking about the magnetic properties? Yes, this is based on the magnetic moments which arise due to the orbital motion and spinning motion of the electron. I hope you understand what I mean, orbital and spinning. See, you have a ball and you're rotating it in the same position. Like you hold a ball in your hand, just twist it left and right. What is orbital? It's revolving around a circle. That is the orbital motion. So if you have some ball here and it is revolving in the own axis in the same point, that is spin. Orbital is what you have a round and this is rotating all over this. These are the two types of rotations that they consider. So as electron is charged particle, okay, as you know, electron is charged particle, the circular motion of this electric charge, whichever electron, is going to cause, electric charge makes the electron act as a tiny electromagnet. Act as a tiny electromagnet. So the magnetic moment of magnetic field is generated due to orbital motion of electron field generated due to the orbital motion of the electron is along the axis of rotation. So the electron also has magnetic momentum, due to spin which happens along the axis, which is directed along spin axis. as you completed. So we understood that the magnetic moment of the electron is due to two things. One, it's traveling in the orbital motion about the nucleus or spinning on its own axis. So for each spin by electron, magnetic moment, magnetic moment is plus or minus mu b. This is Bohr's magneton. What is the Bohr magneton? Bohr magneton, it is a fundamental unit of magnetic moment and whose value is 9.27 into 10 power minus 24 angstrom meter square. The magnetic moment due to orbital motion is ml mu b. What is this? This is magnetic quantum number that we learned of the electron. So, like this, we have so much under magnetic. We have dia, para, ferro, antiferro, ferri, so many magnetics. Can I clear? I'll write here in this. Actually, the magnetic moment, whichever I'm talking about, magnetic moment is a vector quantity. So we know vector quantities now. They are represented by the net magnetic moment of an electron will be represented by okay. That's why they represent by an arrow. So material may be considered to contain a number of magnetic dipoles. Like, you know, every bar magnet will have a north and south pole. Na? Like that, material can have so many magnetic dipoles. Due to this magnetic moment of this magnetic moment whichever is present, the electron is going to of different substances, they behave differently towards any other external applied magnetic field. So based on the way the behavior of electrons or substances when they undergo any external magnetic field, we actually classified or categorized substances into different categories. So I'm clearing the screen and I'll write about each of them. First classification is diamagnetic substance. Write down clearly. Diamagnetic substances are those, they are weakly repelled they are weakly repelled by the external magnetic field. Like TiO2, NaCl, benzene, etc. You know, diamagnetic substances, they have all the electrons paired. Right? These are important things that you have to write under this. Also, they are weakly magnetized. You know, magnetic field in opposite direction. That is about diamagnetic substances. Only these 3 points are enough. Next we have paramagnetic substances. These are weakly attracted. They are weakly attracted by magnetic field. These have permanent magnetic dipoles due to the presence of some species, like what? Atoms, ions, molecules, like that, with unpaired electrons. By the way, very importantly, these substances lose their magnetism in absence of magnetic field. TiO, PO2, CuO, O2, Fe+3, etc. If you let me know that you're done, we'll go for it. Can I clear? So after dia and paramagnetic substances, we have ferromagnetic substances. I think we are all aware of the first two types of substances. So first two types of substances are dia and paramagnetic. So let us look at the ferromagnetic substances. Ferromagnetic substances are those which actually show permanent magnetism. Previously, there were conditions for the exertion of magnetism, whereas this is those which show the permanent. They show permanent magnetism. Even in the absence of magnetic field. Even absence of the magnetic field. These are ferromagnetic, and examples would be metals like iron, nickel, cobalt, and chromium oxide. These four are those which show ferromagnetism. These remain permanently magnetized. These remain permanently magnetized. Once they are magnetized. How does this arise? This arises due to spontaneous alignment. Spontaneous alignment of magnetic moment due to the unpaired electrons in same direction. So I'll show you. This is how ferromagnetism looks like. So this is about ferro. Once you're done, we'll write ferri, like antiferro and ferri. You're done with this? Yeah. So we have the next two. Next we have antiferro magnetism or antiferromagnetic substances. So antiferromagnetic substances are these substances. Substances which are expected to possess paramagnetism or ferromagnetism on basis of the unpaired electrons concept, but they actually possess zero net magnetic moment. Zero net magnetic moment. Example are manganese oxide, Mn2O3 and MnO2. So why is this happening? It arises due to the presence of equal number of magnetic moments in opposite direction. I'll draw the diagram of antiferro. It is like if I have 1, 2, 1, 2 and 1, 2. This is antiferromagnetism. So can I clear? Assume it's done. Next we have ferromagnetic substances. Ferromagnetic. These are expected to possess large magnetism on basis of unpaired electrons, but actually have small net magnetic moments. These are called ferromagnetic substances. Example is Fe3O4. They are weakly attracted by magnetic field as compared to ferromagnetic substances. Oh, these are 5. We are done with this type of properties also. We have dielectric. This is ferro. They'll give you in the exam diagrams also. That's why I'm drawing. They'll ask you, this is ferromagnetic. So once you're done, we are done with two types of properties. We'll also complete the dielectric property. Will be done in like next 10 minutes or 15 minutes. We'll be able to complete. So once you're done with this, let me know. Can I clear? Assuming you're done, we have dielectric properties. This thing is to remember, this today's class, whatever is to remember, write the notes in by heart. So a dielectric substance is something in which an electric field gives rise to no net flow of electrons, no net flow of electric charge. This is because electrons in a dielectric substance they are tightly held by individual atoms. So what happens generally when electric field is applied through these substances? I don't know if I have to write all this, but when electric field is applied, polarization takes place. You know polarization, two poles. Because nuclei are attracted to one side and electric cloud to other side. The alignment of these dipoles may be compensatory, maybe in compensatory way. That is, no, it's like there will be in two ways. One is net dipole moment is 0, or they have a net dipole moment. Because of dipole moment, you have some properties arising. So we'll talk about that. This much is just to understand what a dielectric cloud is. So let me know if you're done. So I'm clearing it, and we actually have like 5 more slides. It will not be done even in 10 minutes. We'll continue with this part, and we are going to solve questions on solid state at least for next 2 classes. And I might plan to give a test in the weekdays or maybe on Sunday on the whole solid state. So I wanted to please put some interest in solid state. It's a very like some 6-7 good topics, and you are perfect with them. You're perfect with solid state. It's not actually very difficult. I hope all of you already started reading it. Thank you and good night. I'll see you again in the next class. We'll continue. Thank you all. We'll have to continue with the dielectric properties. Thank you.